Well, let's continue our discussion with dot products in Rn. Hopefully today we'll get to extend this idea to inner products for any vector space. So last time we motivated why we did inner products in particular. One of the things that we're interested in being able to do is figure out the angle between two vectors. In particular, we want to have a way to check easily if if two vectors are perpendicular to one another. And then we're going to extend that notion of what we mean by perpendicular for arbitrary vectors. We already said that we can check for perpendicularity in the Euclidean sense when the cosine of the angle is 0. As long as you have two non-zero vectors, that can't be 0 on bottom because those are lengths. So the only way this could be 0 is if that inner product piece is 0. Right? And that's exactly what the Euclidean dot product is 0. So we're going to extend that notion to arbitrary inner product spaces in a little bit. Pardon me. But we defined what the inner product is generally for any Rn. Well, the standard inner product or dot product for Rn. And then noticed that using those properties, we get these using that definition, we get these four properties. Doesn't matter what order you do the dot product in. The dot product behaves nicely with respect to adding vectors. I can put a scalar wherever I like. The last one's kind of the big one. It has to do with length. When you do a dot product of a vector with itself, you get something that's non-negative. And the only way you can get 0 is if you started with the 0 vector. Those are kind of the important things of being an inner product. And those are the axioms that we're actually going to use later on to define new inner products on spaces. Okay. All right. So we've already talked a little bit about length. Length, different words for length is magnitude or norm. Because again, we're going to use the same notion of length for any arbitrary inner product space. It may not make much sense to know what we mean by length of a vector if it's a function, right? It may not, or a matrix or what have you, okay? So we're going to define this in terms of the dot product. We've already noticed that we can do it this way. Norm, magnitude, length, those all words mean the same thing. You can define this as the square root of the dot product of the vector with itself. And it's that last, pardon me, it's that last property of the inner product that allows us to do that. I need to make sure that what I'm taking the square root of isn't negative, right? So if I have that last property that says when I do an inner product with itself, I get something that's non-negative, that allows me to be able to take the square root. And we notice that for Euclidean products, inner products, that this really is, not a vector. This just really is the sum of the squares of the components. Why do I keep wanting to make that a vector? And that's what I get for the Euclidean, for the length of a vector in Rn. And we've already noticed that, right? That's just Pythagorean theorem, isn't it? It's an extension of the Pythagorean theorem, but it's just Pythagorean theorem, right? Each of these components gives you kind of the dimension of a leg, and then you figure out the hypotenuse. All right. So using this definition, we can figure out the magnitude of V here in R3. What will we get in this case? Good. We'll do the sum of each of the components squared. 4 squared is 16. Negative 3 squared is 9. 5 squared is 25. We get square root of 50, which is what? 5 root 2? If we simplify. Oh no, that's freaky. I've got my other computer up here, and apparently they're linked because they're logged into the same thing. And it's actually copying what I'm writing over on my other screen too. It's weird. Is that okay? Doing those? Yeah, I'm guessing if you've seen vectors before, you've done this. This should not be a new concept. Okay. All right. So a couple of the other another property that we have for magnitude. Again, we want to. The idea behind this is that we want to extend this to hopefully arbitrary vector spaces, but in particular some certain vector spaces. Like I mentioned the other day, the point of a lot of this is to be able to approximate nasty functions with nicer functions. Okay? So we need to have some way of knowing what's the best way to do that, in some sense. What's the best possible way to do that? Okay? So, in general, this idea of length may not necessarily make sense as what we think of Euclidean length. Okay? However, our intuition says, I want to think of this magnitude as being length of a vector. Well, if I multiply a vector by a scalar, what should that scalar do to the length? If it were, say, the scalar were 2, what should happen to the vector? It should be 2 times as long, right? If I multiply it by a half, it should be half as long. What happens if I multiply it by negative a third? It points the other way. What happens to the length? It should just still be a third as long, right? So what we should get here is that C should pop out, but I have to be a little bit careful because lengths are positive. So when I pop the C out, I really should get an absolute value on it, right? The negative, again, just points it in the other direction. That C, that absolute value of C part really is what's changing the length of it. This should work, hopefully, in any vector space. So let's see if we can prove this for, not any vector space, for any vector space that has an inner product defined on it. We refer to those as inner product spaces when we talk about that later today. Okay. Let's see if we can prove it generally versus using the specific standard inner product. Okay. So what I mean by that is I want to prove this by using this definition of length. Okay. And some of the other properties that we have for inner products. So if I want the magnitude or the norm of that vector, according to the definition, I'm going to take the square root of what? So I don't want to use this part. I literally just want to use that. Yeah, the CV dotted with the CV, right? The definition is the square root of the dot product with itself. All right, that is the definition. So that's how I want to do it. Okay. What you said would work for Euclidean inner product. Okay. I want to try to do it generally if I can. Okay. Now let me scroll back up. Using this property, where it says that I can take the C if it's here and move it to the front, or I can take the C if it's here and move it to the front. How can you rewrite what's underneath the square root? I can take this, I can take this C out in front and that C out in front, right? Using that property twice. And so you'll get C squared times V dotted with itself. Inner product is a scalar. Inner product is a real number. For our purposes, inner product is a real number. So I've got a product of real numbers and I'm doing the square root. Square roots behave nicely with respect to products, don't they? As long as they're real. And a little weirdness if they're not real. There's a little weirdness if they're negative. As long as they're positive, it's okay. But this is non-negative. This is non-negative, and so is that. Okay. So I can break it up. The second piece, looking at what I put in that red box again, that second piece is the definition of what? This part right here. It's the definition of what? Yeah, the length, right? That's the length of V. The first part is the square root of c squared. What do you get when you take the square root of c squared? Gotta be a little bit careful. If c is negative, I get absolute value. Yeah, it better be absolute value because that's what we're trying to prove, right? Okay. Remember, when you square a negative, the negative goes away, and you take the square root, it doesn't come back in again, right? So it stays positive. So it really is absolute value. Okay. So this property of magnitude is true for Euclidean inner product, and you could have used the definition up here of your Euclidean inner product and got the same answer. Okay. But it works for any inner product that we could come up with. Okay. So it really is a property of magnitude, not just a property of real vectors, Euclidean vectors. Questions on that at all? That one was not too bad of a proof, was it? That one was pretty short. Okay. All right. What do you think it means to be a unit vector? Well, just in general, I mean, if it's going to be a unit vector, what should be true about its length? It should have length 1, right? Good. So a vector is called a unit vector if the magnitude of that vector is 1. So this example that we're talking about here wants us to try to find a unit vector that's in the same direction as 2, 2, 1, 1. But what is the magnitude of that vector? Start there. How long is that vector? Okay, yeah, so we'll do this. Square root of 2 squared plus 2 squared plus 1 squared plus 1 squared, right? And we do get square root of 10. Okay. Well, that's not equal to 1, right? So that is not a unit vector. But if I want to create just any vector in the same direction, what would I multiply this vector? Now, not worried about unit vector, but literally just any vector that points in the same direction as v, what could you multiply it by? Okay, well, that's for the unit part. But I just literally, if I just want to keep it in the same direction, you're right for finding the unit vector. If I just want to keep it in the same direction, what kind of a number would you multiply it by? Positive, right? A positive scalar, right? If you were looking for the opposite direction, what would you do? Make it a negative. Good. All right. So since I want it in the same direction, I probably want to multiply it by a positive value, right? Now I want to, instead of having length root 10, I want it to have length 1, right? Using this property that we just proved above, I should be able to multiply it by a scalar to turn that into a length 1, right? And a couple of people already mentioned what scalar you need to use because you've seen it before, right? If I want to change the root 10 into a 1 by multiplying by something, what should I multiply by? 1 over root 10, right? So the magnitude of 1 over root 10 times v, I'll just do it with the number to start with. According to the property we proved earlier, I can pull that scalar out. There's no negative, so I don't have to worry about the absolute value, times the length of v, right? And notice in that case, my root 10s will cancel. So I really do create a unit vector in that case. So our unit vector, which I'll refer to as u here, will be 1 over root 10 times the vector we started with. And like I said, I've heard a couple of people already mention this. In general, if v is not the 0 vector, then 1 over the magnitude of v times v is I'll say even the unit vector in the same direction as v. If you wanted the unit vector that's in the opposite direction, you would put a negative in front. Questions on that one? Is that okay? Not too bad? All right. Let's talk about abstracting, because again, we're going to try to abstract these things when we get to more arbitrary inner product spaces. Let's see if we can talk about what we mean by distance between two vectors. That sounds a little bit weird because when you think about vectors, generally speaking, usually you think about them all starting at the origin and then pointing out, right? Something like that. Okay. So when we say distance between vectors, that's not really what we mean. We mean distance between the tips of the vectors. Okay. So this distance from here to here is the distance between u and v. Okay. That's really what we mean. Pardon me. So we denote it with that d of u. Now remember, when vectors, I can create a new vector from those two one way or another. How can I get a vector that's up here if this is u and this is v? How do I find that one that's up there? U minus v would point that direction, right? Or v minus u would point that direction, either or. Okay? Right? So the distance between u and v is defined by the magnitude of v minus u, or either way, you should be able to use u minus v. How do I know that those two things must be equal? Regardless of the fact that I'm defining something that says the word distance in it, how would I know that this is the same as that? Without doing any work at all, how do I know those are the same? Well, the components will be squared. So for Euclidean vectors, those will always be the same because it will square the components. So if I flip the direction, all I did was make it negative and I squared it, make it positive, right? But if I want to do general inner product spaces and not lean on the Euclidean part, what's true about those two vectors? What are they? How do I get from one to the other? Okay, they're facing the opposite direction, so they're the opposites of each other, right? What's another way to write the opposite of that using a scalar? -1. Good. And what happens when you pop that scalar out in front of a magnitude? What do you do to that scalar when you put it out in front? Take the absolute value. It becomes a 1, doesn't it? Right? So this is going to be, no matter what I do, no matter what inner product space I am in, when we get to that point and make new direct dot products or new inner products, that's still going to be true. I can do the subtraction in either order. It doesn't matter. I should get the same distance between those two things. Okay. All right, so if I want to find the distance between these two vectors in this case, the first thing you're going to do is subtract them. Again, it doesn't matter the order that you subtract them in, because like Austin said earlier, especially for the Euclidean, I'm going to square the components anyway, right? So if I do u minus v, what do we get?
7, 1, 7.
Good. 717. So if I want the distance then between U and V, oops, we'll do the magnitude of 717. Seven squared is 49, so you'll get what, 99 when you add these together. And again, if you want to simplify, that's 3 root 11. So again, in general, doesn't matter what inner product space you're in. If you want the distance between the vectors, that's defined as subtract them and take their length. Okay, take the length of the difference of the two. All right. So what are some properties of distance that pop up? Okay. Pardon me. Well, the first one, basically these properties of distance follow from the direct, I keep saying direct, the dot product axioms that we have. The first one is, we've already seen it. Doesn't matter if I do the distance from U to V or the distance from V to U, I get the same answer. Makes sense that should happen, right? Right? Shouldn't matter which way I go. If I start at point A and go to point B, it better be the same as if I start at point B and go to point A. Right? The other one says that distance is always non-negative, and the only way the distance can equal 0 is if the two vectors are the same. This is literally just a restatement of that fourth property of dot product. Remember the dot product property, the fourth one said that if you take a dot product of a vector with itself, it's always non-negative, right? That was the first part. Well, the distance is defined in terms of length. Length is determined, jeez, I can't talk. Distance is defined in terms of length. Length is defined in terms of dot product with itself. So it has to be non-negative, right? So that's why that's true. We said that the only way a dot product with itself can be 0 is if you started with the 0 vector, right? Notice in this case, though, when you do distance, what vector are you taking the dot product with itself to get 0? Or what? I'm sorry, not in general. In general, what are you talking about here? What vector are you taking the dot product with itself? It's the v minus u, right? If that turns out to be 0, then you had to use v minus u as the 0 vector, or the u and the v with the same vector to start with. So again, this second property is just a consequence of that fourth property of inner products. And you want it to be that way, right? The only way that you can have a distance to be 0 is if you didn't move anywhere. That's basically what that says. All right. Let's see if we can finish this off and then go to the next little handout that I'll have for you today. So this is just kind of tying up everything that we talked about. Remember, we have a formula for angle. We said that the cosine is equal to the dot product over the lengths. What is the dot product of those two vectors in this case? So yeah, you do the negative 12 plus 63, right, on top. 4 times -3 plus 9 times 7. On bottom, what do you get for the lengths of each of those? Length of u is going to be 4 squared plus 9 squared. 4 squared is 16. 9 squared is 81. So we get 97. Is that right? For that one? The other one you'll get 58. Good. And that is a product of those two things. So we've got 51 over the product of those two things. So I wouldn't expect you to simplify that. So if I want to figure out what the angle is, what would you do? Inverse cosine. Good. Whatever that number turns out to be. However, looking at that value without putting your calculator or anything, is this going to be an acute angle or an obtuse angle? Certainly not a right angle because it's not 0, right? Is it an acute or an obtuse? Here's an example of an acute angle. Here's an example of an obtuse angle. What can I say about the cosine of that angle? The cosine of it. Certainly less than 1, but it's also greater than -1. What can I say about the cosine of this angle versus the bigger one? The bigger one's negative, right? If it's obtuse, it's negative, correct? That one's positive, right? When first quadrant versus second quadrant, right? So now go back and look at that. Tell me, is this going to be an acute angle or an obtuse angle? It has to be an acute angle, right? It has to be acute because it's that what we're doing the inverse cosine of is a positive value, right? By the way, what tells you if that expression inside the parentheses there, which is right there, what tells you whether that's going to be positive or negative? Is it the dot product or the lengths? It's the dot product because the lengths are always positive, right? So the angle will be acute if your dot product is positive. It'll be right if it's 0. It'll be obtuse if it's negative. I don't have to do any work on the calculator from that point. Okay. Now, if I actually want a quantity for that, I would need to do it in my calculator. I don't feel like trying to think about it in my head. I'm not going to. I'm trying to think about how big it might be. 97 is about, well, square root of 97 is a little bit less than 10. 58, 64, so that's a little bit less than 8. So let's see, that's a little bit less than 80, so that's a little around 0.6-ish. Oh, so bigger than 45, maybe around 50 something. I don't know, just guesstimating. What's it? 40.5? Did my estimate wrong? It's possible. Cosine of 45 degrees is 0.7. 0.707 because the square root of 2 over 2. So anyway, it's fine. Whatever. That's what a calculator is for. Okay. What's it? Oh, gotcha. Yeah. Like I said, you should be able to put in a calculator. This is about 50. The bottom's a little bit less than 80. So 0.6-ish range. So it should be bigger than 45. 48? Yes, I said it's about 50. So I said to start with, wasn't it? Yeah. Okay. All right. Anyway, let's start this one by just taking the dot product to begin with. What is the dot product of these two vectors? Okay, it's going to be 0, right? Because you get 6 times negative 2 plus 1 times 0 plus negative 4 times negative 3. You really do get 0, right? Do I need to do any other work? No, because once the dot product is 0, that fraction is 0, isn't it? As long as you start with 2 non-zero vectors, right? Starting with a 0 vector would cause problems in the denominator. But as long as you start with 2 non-zero vectors, if I get a dot product that's 0, I automatically know that my angle is 90 degrees. I don't have to do any other work. Okay. All right. So this leads us to our last little definition that we have here. It's the idea of being orthogonal. Orthogonal is a fancy word for perpendicular. But we want orthogonality to make sense regardless of what type of vectors we're talking about. Perpendicularity is a Euclidean concept. Okay? But not all of our vectors are Euclidean vectors. In particular, we're going to be interested in vectors that are functions. Okay? Functions being perpendicular may not make much sense as far as what we're talking about. Okay? So why we use a different word we refer to as orthogonal, but we want that same concept of being perpendicular-ish based on some properties that we'll want to have later on for quick computations of things. So that's the idea. Anyway, that's our definition of orthogonal. Any questions at all about anything we've talked about so far? The computation's okay that we're doing? Okay. All right. So let's see if we can abstract this a bit. To general, what we refer to as inner product spaces. Inner product is just a fancy word for dot product. So we're not changing a lot in regard to that. Whatever we're trying to say. Okay. I don't think I put this one in here. I gotta insert. I did it on the other computer, but the other computer wasn't working. All right. So, how did we motivate dot product last time? The very, very first thing that we did. Very, very first thing we did was figure out an expression for angle, right? Okay. So that's our main purpose of assigning an inner product is to define angle measure between two vectors. Right. To give a little bit of a hint as to why we might want to do this, what do you use for standard basis for R3? What do we use? Not a trick question. What do we use for the standard basis? No. Yeah, it was 1, 0, 0, 0, 1, 0, 0, 0, 1, right? Use the 1 in the first component to generate your x coordinate. Do the same thing for the y coordinate. Do the same thing for the z coordinate, right? Okay. If I had some other vector that I wanted to try to find the coordinates of, I can read them easily off of there. But notice that I can also get coordinates by doing inner products. So for example, what I mean by that is, remember we also talked about the concept of coordinates with respect to a basis, right? If I have a basis, then I want to know what do I need to multiply by the first vector, what do I need to multiply by the second vector, by the third vector, so that when I add them together, I get the vector I'm interested in. Well, one way to do that, if you've got a nice basis like this is the standard basis, so it's going to look a little silly what I'm doing, but it'll make sense later when we get through all the material, okay? If I want to, that was weird. If I want to find the coordinates, I can do this with dot product. I can find the first coordinate by simply taking the dot product of the vector with the first element in my basis, right? I can find that coordinate, right? I can do the same thing to find the second coordinate by dot product, taking the dot product with the second vector in my basis, and then do the same thing for the third one. When I've got a basis that's set up like this, and there's two qualities that this basis has that we have to have in order to be able to do this. Notice that each vector has length 1. Each vector is a unit vector, right? Okay. Also notice that if I take them two at a time, they're always orthogonal. We call that pairwise orthogonal. Okay. What we have is what's referred to as an orthonormal basis. Okay. And orthonormal bases are nice because I can get coordinates for vectors relative to those bases by just doing dot products. That's where we're headed with all this stuff, by the way. Okay? There's a reason why we do all of this stuff. Because we're trying to get to that point. All right? So anyway, this is why we care about angle. If I can define angle, I can define orthogonality. From orthogonality, I can create nice bases to use to do computations more quickly. That's the idea. Okay? So anyway, that's why we care about angle measure. Now, along with angle measure, we get things for free like length, like distance, right? But angle measure is kind of our motivating factor here. All right. So we're going to define, like what we did for when we did abstract vector spaces. When we start talking about inner product spaces, we're going to talk about some dot products that aren't standard. Okay. If I want to define something that's not standard, then I need to check that it really is a dot product. Okay. So when we talk about, remember for vector spaces, we had those 10 axioms. Okay. Dot product axioms are a little bit shorter. There's only 4. Okay. But they're the 4 properties that we talked about that the Euclidean dot product has. Okay. So those are that you want. Oops, sorry, I forgot. Let me make sure I'm using that notation. Yep. So by the way, they changed the notation to you on you as well. They use these pointy brackets around the vectors. I almost forgot. Pointy brackets around the vectors separated by a comma tells you you're doing an inner product. So for inner products, the order should not matter. I should distribute over vector sums. I should be able to move my constant wherever I want. Oops. If I've got a constant multiple of a vector. And that last one says that if I do an inner product with itself, I should be non-negative, and the only way that it can be 0 is if I started it with the 0 vector. Okay. Those are our 4 inner product space axioms. If something weirdly defined, which, by the way, we're not going to do a lot of weird defined things. They're going to be actually relatively normal defined things for the things that are going to be useful. It'd be kind of things that you would want to define an inner product as. But again, if we're going to define something weirdly and claim that it's an inner product, it has to satisfy these 4 things. Okay? So let's see if we can do an example of something that's new and different. Let's say we want to define an inner product on our polynomials of degree 2 or less. So I'll start with an a naught x squared plus a b naught x plus a c naught. Do the same thing with a q of x, but call them a1, b1, and c1. And then define my inner product as multiply your x squared coefficients together, multiply your x coefficients together, multiply your c constant coefficients together, and add them. Before we even start, what dot product does this look like? This should look very familiar. We just did it in the last section. It looks like a Euclidean dot product, doesn't it? What if I did the vector a naught, b naught, c naught, and the vector a1, b1, c1? Doesn't that look like a Euclidean dot product? Yeah. Okay. All right. We're just defining it for other polynomials here. Pardon me. All right. So again, if you wanted to go through the process of showing that this is an inner product, I'm not going to do all of them because, again, it's just a matter of doing the formulas. You would need to go through, you're trying to show equality on some of these things, right? Okay. So do one side, do the other, and show that they're equal, right? So for example, let's say we start with, let's do the second one, where we've got the inner product of one polynomial and the sum of 2 others. And I'm just going to use a subscript of 2 for my second polynomial. So I'll do an a2x squared, a b2x, and a c2. What operation do you do first here? The first thing I would do is add, right? These are polynomials, so we'll add like terms. So your A1 and your A2 will get added together. Your B1 and your B2 will get added together. And your C1 and your C2 will get added together. That's just combining like terms, right? How is your inner product defined on this particular space, the way we've defined it? What do we do? Yeah, multiply coefficients and add them, right? So we'll have an A naught times A1 plus A2. We'll have a B naught times B1 plus B2. We'll have a C naught times C1 plus C2. Let's look at the other side of the equation for that second property. We need to do the inner product of P and Q, the inner product of P and R, and add. Your P is A naught X squared, B naught X, and C naught. And then same idea, but with ones for the C. And then the second inner product involves the R. That one had the subscripts of 2 on it. Now, in this case, we'll do the inner product next, right? The inner products next. In the first one, we get what? When we do the first inner product.
A naught A1 plus B naught B1 plus C naught C1.
Good. And in the second, we'll get
B naught B2.
yeah, the A naught A2, B, yeah, I skipped one. B naught B2 and C naught C2. Are those two things the same? Yeah, I need to do a little bit of a rearranging, but if I combine those two things together, don't I get the same thing as I got up here? Right? If I combine these two together, I get the same thing as I got up here. And if I combine those two things together, I get the same thing I got there. So they really are equal to each other. So I'll just write it that way to start with, or to end with, I should say. Oops. Okay. Questions on that one at all, that part? Again, this is one part of 4. To show that something is an inner product, it has, just like vector spaces, it has to satisfy all 4 properties. Okay? So if it's going to be an inner product, it has to satisfy all 4. Now, I said that this one's not particularly weird because if we think about our polynomials there, they look like Euclidean vectors, don't they? So it's not particularly weird. Okay? This one might look weird on its face, but if I'm doing functions, continuous functions, integration is kind of a natural thing to do. So is differentiation, but integration is kind of a natural thing to do, right? Now, why might I not want to use derivatives? Well, derivatives, I can differentiate something and it becomes 0, but it didn't start with 0. So defining an inner product using a derivative would be a difficult thing to do. Not impossible, but more difficult, right? Because if I differentiate something, I might get 0. And we said, though, that the only thing that you can take an inner product of with itself and get 0 is if you started with 0, right? So doing it with the derivatives is a little bit tricky, okay? But integration is a nice thing because if I integrate as long as it's continuous, if I integrate a non-zero thing with itself, I'll square on the inside, which means it can't be 0 unless it was literally the x-axis, right? So this integration formula for doing an inner product is a pretty good way to do that for function spaces. So we'll talk more about this next time, I guess on Monday.